Today I'm going to share some things we've been working on doing some type of reasoning with diffusion models as well as with energy-based models. So maybe some high-level motivation. So when we think about reasoning, I guess we typically think about large language models. And when we look at large language models in combination with some chain of thought, which tells the model to decompose a problem, propose, check, and revise. This type of reasoning really allows you to generalize and solve pretty complex problems that if you just directly ask the LLM to generate a final response, they're not really able to do. One question is, if we think about domains outside of natural language, for instance, I'm very interested in robotics. Now we have some language instructions, and we want to compute a set of actions, let's say to move up the stairs in this house. An issue is this is in some type of continuous space, so it's not as clear what you would do to, what would be the intermediate computations you would use to do reasoning. So what I'm going to talk about is one potential approach to just doing reasoning across a wide variety of domains that are not language. And the overall idea is that we're going to try to learn some type of energy function. So why is the thing you want to predict? And then you have this energy function that scores every single possible prediction, y. And then your final prediction is essentially going to be the solution that minimizes this energy function that you're going to learn. So your neural network is going to take in the problem specification x as well as some possible solution y. And it's going to output a scalar energy E here. That's a single real number. And you can either try to deterministically optimize this energy function to find the minima, or you can try to learn an energy function that represents the entire probability distribution. And then you want to sample for many different plausible solutions by sampling from this distribution here. And essentially, we're interpreting reasoning as some type of iterative inference on this energy function. So reasoning corresponds to either directly using some type of gradient descent to optimize this energy function, or trying to sample from this overall distribution. And if we look at how we typically solve problems, so typically we have some type of direct neural network that takes in some condition. The neural network outputs, does some computation on this condition, and just directly generates your final answer. And in contrast, if we have this more energy-based perspective on reasoning, what we do is now we have a neural network that takes in the input question as well as a possible solution, and the energy function outputs a final score. And now your goal is to find some answer that minimizes energy. And you can imagine two processes. So you can imagine one possible solution, which is y1 here, which gets an energy value of 2.8. You can imagine another prediction, y3, that gets an energy value of 1.7. So these are just random guesses of possible solutions. But you can take your previous solution that had a solution of 2.8, and you can try to revise it. And this can get you a solution that has lower energy. And so essentially, the second type that I'm talking about here with the energy function allows you to use some type of search to implement your reasoning and to get your final answer. And there's a general thought that perhaps learning this energy function, since it corresponds to some type of verification with checking whether the answer is correct or not, this is maybe easier to learn for complex problems than directly generating the solution in a single pass, which you typically do with a neural network. And another nice aspect of this type of energy parameterization of reasoning is if you want to solve some complex task, maybe you want to optimize for a trajectory that reaches a particular goal, and you also want the trajectory to satisfy some type of physics constraint, you can directly optimize the combination of these two constraints in order to solve your task. So this type of specification of writing the problem you want to solve as this energy function allows you to compose multiple different energy functions to solve more complex tasks also. And the final thing is this type of interpretation of using some type of, I guess, optimization on this energy function to implement reasoning gives you a bunch of different ways to scale up your inference time compute. So you can imagine running more steps of optimization. You could use different types of optimization algorithms. You could have a number of different parallel samples that you use to run optimization. You could do different types of restarts. You could also do some type of global search. So there's a number of different ways of implementing reasoning under this interpretation that reasoning is optimizing some type of energy function. OK, so that was a broad intro. Let me know if there's any questions. But essentially, so that was the overall motivation. What I'm going to talk about next is I'm going to talk a bit about first how you actually train these energy-based models, including how diffusion models are connected here. And then I'll talk a bit about how we can use these energy-based models for reasoning. Second, I'll talk a bit about how we can do different types of high-level reasoning algorithms for different types of search on top of this energy function. And finally, I'll talk a bit about how we can compose multiple energy functions together to solve more complex problems. Yeah.
Just want to clarify, so during this reasoning phase, do you actually interact with the environment, or it's just do it like compute and not doing exploration?
Yeah, you don't interact with the environment. So this is all compute in your model. You can imagine that your model has some simulation of what the environment looks like. So then you can do some simulated rollouts. But yeah, you don't actually interact with the environment.
So in some sense, to use this, you have to do something like model-based learning, reinforcement learning.
Well, yeah, you can view this as kind of like the energy function is learning a model of the world. So you're doing some type of model-based inference to make your decisions.
So it's just one model, right? It's not like multiple models that are.
So you could have each model construct one energy function. You could compose multiple models together. So it doesn't have to be one model.
Oh, it's all like trained end to end.
Yeah. Well, so you could train the energy function end to end, but you could also have energy functions from different parts that you combine together. So the last part of the talk will have multiple different energy functions combined together to make your decisions. OK, great. So first, let me just talk a bit about energy-based models. So here's the intuition of the energy-based model. Let's say I wanted to learn an energy-based model for red trucks. So essentially, I have a neural network that takes in different images. So if I have an image of a green truck, this neural network is going to assign it high energy. And in contrast, if I have an image of a red truck, the neural network will assign it low energy. And this energy function is essentially going to construct this landscape across the space of all high-dimensional images so that all images of red trucks have low energy, and all other images have high energy. And our goal is to essentially learn some type of probability distribution using this energy function. So we're going to convert this energy function to a probability distribution through the Boltzmann distribution. So essentially, we want to learn an energy function such that the probability distribution P of x can be represented as e to the negative energy. And to effectively, so you can, so if you look at the space here, the energy function is pretty high dimensional. It's fairly hard to sample from this distribution. So what we're going to use as a tool to sample from this distribution is going to be Langevin dynamics. OK, so in terms of learning energy functions, so the simplest way to do energy-based model training, and this has been around for many decades, is to essentially do some type of contrastive training, where on one hand, you have a term where you decrease the energy of ground truth data. And on the other hand, you have a second term where you try to increase the energy of these samples from your model distribution. So you have this contrastive procedure where you decrease energy of real data while increasing the energy of samples from your distribution. And then we've been working on trying to scale these energy-based models to high-dimensional domains for a number of years. And one approach that we found to be somewhat effective was to use some combination of Langevin dynamics and some replay buffers. So let me just illustrate a graphical illustration of energy-based model training. So at the beginning, you have this energy landscape where all images, both these images of red trucks as well as Gaussian noise, they get all assigned the same energy value. And now you have this contrastive procedure where you decrease the energy of real data. So you decrease it, so these green points get moved down, while whatever samples you drew from your model, which is this noise, you increase the energy of those samples. So now you have an energy landscape that has lower energy at ground truth data. What you do afterwards is now you repeat this procedure where you have a more evolved energy landscape. So again, you take these ground truth images and you decrease energy of these ground truth images. But at the same time, you take some samples. So you draw a sample from the new energy landscape, which now is a bit more evolved. So the images look a bit more like real red trucks. And you just repeat the procedure where you decrease the energy of those negative samples, which are in red, while decrease the energy of the green samples while increasing the energy of red samples. And then you just repeat this procedure until finally you have a new energy landscape where now the only minima of the energy landscape are essentially red trucks. So at this point, you decrease the energy of red trucks and you increase the energy of red trucks also. At this point, essentially training ends because you're decreasing the energy of red trucks and increasing, so they cancel out. So you just repeatedly do this procedure until you converge to this fixed point where the energy landscape has low energy exactly at red trucks. Yeah, and then so sampling from EBMs ends up looking fairly similar to diffusion models. So like I said a bit earlier, this is, you have this Langevin sampling procedure where you start with Gaussian noise, and then you run this Langevin procedure. So this was our work in 2019. So this was a long time ago, so the samples don't look that good. So these are pretty poor samples. Recently, we've actually been just scaling the same algorithm. So we just take the same contrastive training algorithm, we apply it to a transformer, we train it for around a month. We had some of the new generative modeling tricks, and we find that you can get this contrastive algorithm to work pretty well on 256 by 256 ImageNet. So we get a FID of 3.82, and here are some of our images. So we're pretty confident that this training procedure can also work on more modern generative settings also. And then, so why did I mention diffusion models? So diffusion models, I guess everyone's probably very familiar with this. So a diffusion model essentially learns a sequence of score functions. You can interpret each of these score functions as parameterizing some type of EBM. So you can, and in principle, you could imagine that when you're parameterizing these denoising functions or score functions, you could just parameterize them as a gradient of an energy function. So you could have a neural network that explicitly predicts the energy, and then you just train the gradient of the energy respect to the input as your denoising function, and you just train that with the denoising loss. And then you can kind of, I guess we're all very familiar with the diffusion sampling procedure, but you can write the diffusion sampling procedure as essentially a Langevin, like Langevin sampling at that particular noise level, plus some contraction to the next noise level. So you can actually interpret it as just a single step of MCMC sampling on some tempered distribution. So essentially a lot of these EBM operations you can kind of like interpret diffusion models as also. And one thing we've been trying to do is we've been also trying to get a bit more of a bridge between these diffusion models as well as energy-based models. And this is on the left, this is an illustration of some of the energy landscapes that you can get, or like some of the vector fields you get from flow matching. So you can see that if I want to generate a sample where these are these 2 points here, flow matching initially just learns this Gaussian attraction field, and then over the different time steps, it learns these local refinement fields that eventually converges to these ground truth data points. So what we want to do in equilibrium matching is we want to use some type of flow matching procedure to learn some type of like a vector field that corresponds to some energy field, such that when you run optimization on it, you gradually converge to ground truth data points, which are shown in the blue star. And the idea is that we essentially just take the flow matching loss that's typically used, but what we do is we just add a term where we add the decay term. So we make the target of the flow matching model be the normal flow matching loss, but then at some point alpha to the time step 1, we have this decay term where we just make the target closer and closer to 0. And what this does is it makes, and also the other thing we do is we get rid of the time step in the flow matching procedure. And finally, the third thing we can do is we can just parameterize this flow matching as the gradient of the energy function. So we can actually explicitly have a neural network that just predicts the energy. And if you do these 3 things, essentially you're able to construct the energy landscape where the minima, where the gradient is 0 at the ground truth data points. So essentially you learn some type of attractor landscape in the energy space that allows you to converge to these ground truth points. And then in terms of how you actually sample from these models, you will just initialize some generation from Gaussian noise, and then you can run some type of gradient-based optimization, and then you can just stop when the magnitude of the energy function is below some value g. And then we have some proofs of some idealized assumptions, but essentially what it states is that with this loss, if you, at the ground truth data, with pretty high likelihood, you can have the gradient of the energy be 0, and you can show that unless the data is in a very pathological way, with pretty good likelihood, all the local minima that you get from shaping the energy function lie on the ground truth data. And in terms of FID, we can get pretty good FID with this approach also. Okay, so that was a brief primer about just training different types of energy-based models. I'm going to move to actually using energy-based models from reasoning now. Are there any questions? Okay, good. Okay, so now let's go back to actually trying to do some type of reasoning with these energy-based models. Okay, so it's a pretty simple motivational question. Let's say I want to train an energy function for adding matrices. So essentially, this energy function takes in two matrices, which is X. So these are just a 20 by 20 matrix where we're just visualizing the values as continuous values. And our goal is to get a final prediction Y that corresponds to the sum of these two matrices. And the way our energy function is going to work is going to take the two concatenated matrices as well as a possible solution, and it's going to output a single scalar energy. Where if the answer is incorrect, the energy is going to be high, and if the answer is correct, then the energy is going to be low. And like I said earlier, now to solve this reasoning problem, we want to find a prediction Y such that the energy is minimized. And the way we do this here is we essentially just do a gradient descent procedure where you start your, some guess here at Gaussian noise, and then you just run this gradient descent procedure to get to the minimum. And actually, it turns out, because in this reasoning problem, there's a unimodal answer. Like if you want to add two matrices, there's only one ground truth answer. There ends up being a slightly simpler energy-based training procedure that you can do. What you do is you just you take your ground truth questions, so X, and then you just start your solutions Y from some uniform noise. And then you just run gradient descent from this random guess until you get to this final prediction that minimizes this energy. And you simply just backpropagate through the optimization procedure on the energy function. So since you know that there is one ground truth solution Y, you simply just run backpropagation through the optimization procedure of Y underlying the energy function, and we use that to directly train the energy function. And this only works if your solutions Y are unimodal. Otherwise, you need to do some other algorithms, similar to the different EBM training procedures I talked about earlier. And then reasoning is pretty easy. Reasoning, you just start your solution from some type of uniform noise, and then you can run some type of gradient descent procedure until you get to a minima. You could also imagine having multiple different random starts. So you could have many different solutions Y from random noise, and then just run gradient descent and choose the one that has the minimal energy across all the iterations. What we find with this type of approach is for a number of different matrix problems, we find that so let's say you have two 20 by 20 matrices and you want to compute the addition of those 20 by 20 matrices. This is a problem that's really easy to do if you just have a neural network that takes in the two inputs as well as a predicted solution, because it can just directly verify if the computations are right. But this is a problem where if you actually just give two 20 by 20 matrices and ask MLP to directly output the sum, this is hard for it because you have a lot of entries that is hard for the model to compactify. But for these local verification, for these matrix operations, we actually find that this type of optimization is pretty helpful for solving the problems. And this is also true for some of these graph tasks, where again, for these graph tasks, like if you want to compute the connected components, the shortest path, or you just simply want to copy some edges for the input edges to some output edges. Again, these are computations where if you have the neural network taking both the input problem specification as well as a solution Y, having the model verify whether the answer is correct or not is pretty simple. And if we look at the actual correspondence between the energy values as well as the actual errors, we find that as the solutions get further and further away from the ground truth answer, the energy correspondingly goes up as the solution distance goes up. And then one thing that we find that's interesting is that this gives us some nice ways of being able to use more computation to get better solutions. So we train our models on graphs of size 10, and then we want the model to work on graphs of size up to 30. And then what we find is if we try to use some type of recurrent network on these large graphs, I guess we only trained on graphs of size 5 to 10, but we find that as these recurrent networks, when you apply them to these very large graphs, then the error continuously goes up as you run more and more computation steps. In contrast, when you have this type of optimization-based prediction, when you run a total, even when you apply it to size 30 graphs, because the model is just kind of computing these local terms on whether the inputs are consistent or not, as you run more steps of optimization, we actually see that the error still continuously decreases. OK, so that was an example where we learned a single static energy function. So instead of learning a single static energy function, you can again do the diffusion analogy where let's say you want to solve more complex problems. And if you want to solve more complex problems, you don't necessarily want to learn a single energy function because this energy function might not be so smooth. You might be susceptible to local minima. So this ends up looking very similar to diffusion models. But essentially, we can instead, to solve a reasoning problem, learn a sequence of different energy functions from the first energy function all the way to the kth energy function. And here we have a combination of two losses. So first to supervise, and then the overall idea is if I want to solve a problem, I'm going to first optimize and find the minima of the first energy function. And then I'm going to use whatever guess I get from optimizing the first energy function to start my optimization for the second energy function. And I'm going to just repeat this process across all of the k energy functions. And the way I'm going to do this is the first loss is essentially denoising and score matching. So I'm just going to add some noise to the label y. And I'm just going to supervise the energy function to be able to decorrupt the label y. And the second one is I'm going to have some type of contrastive loss similar to this approximate maximum likelihood loss I talked about earlier, where I'm going to try to decrease the energy of ground truth answers while increasing the energy of incorrect answers. So I'm going to have a second loss that just tries to locally shape the shape of the model, shape of the energy function so that the correct answers have lower energy. And now when I have this set of energy landscapes, I'm just roughly going to, like I described, so to train each of these energy functions, I'm going to sample some noise level k, and then I'm going to train the energy function with this denoising loss at that noise level k. And I'm also going to train this energy function with some type of contrastive loss, at that noise level k. And then for prediction, it's roughly what you do is you have your initial prediction, which you sample from Gaussian noise. You run some type of gradient-based descent at a particular landscape k, and then you use your prediction at the final answer you get after running your gradient descent procedure to initialize your optimization at the next time step. And then you can do some type of scaling to ensure that everything is in the native scale of the energy function. And then we find that essentially this type of approach where you have a set of energy functions, which ends up being very close to diffusion, gets a little bit of performance on these matrix tasks. We also find that, it's able to do these Sudoku tasks. So it's able to solve these Sudoku tasks on the test data set with close to 100% accuracy. And then what we find is that if we make these harder Sudoku tasks, so these tasks, we have fewer entries of the Sudoku grid that are given, we also find pretty good generalization there. And here's an illustration of this. So if you look at the solutions you get when you optimize the first energy landscape, they have a lot of ones, so it's pretty invalid. But as you sequentially optimize with respect to each of these landscapes, you gradually get to solutions that are much more accurate. And yeah, in terms of generalization performance, what we find is that, so if we on the test data set, so we train the model on Sudoku problems with a fixed number of entries missing. If we test it on the Sudoku problems with the same number of entries missing, then we find that the performance increases marginally as you run more optimization steps, but it doesn't increase that much. It's pretty close to 100. But we find that for problems that are harder, so these problems are problems where we're given fewer entries at the Sudoku board. Then as we run more steps of optimization, we see that the performance does get quite a bit better. Okay. And then finally, the last thing I'll talk a bit about is how you can actually, or the last thing I'll talk about in this part, and then the other two parts are pretty fast, is that you can actually do this type of reasoning with large language models also. And the idea here is to do reasoning with a large language model, I'm gonna take an energy function that corresponds to the negative log likelihood of the language model. And now the distribution that I want to sample from is essentially some tilted or some lower temperature version of the distribution. So essentially, I want to sample from the distribution negative alpha times energy of x, where energy of x is the log likelihood of the language model on your sequence. And one way to think about it is if p is the original distribution my language model has modeled, I want to draw samples from the distribution p to the alpha, which is shown in the orange here. And one thought is if we draw samples from this distribution p to the alpha, this will accentuate things that the model is very confident in. So you can imagine that this can improve the reasoning performance of the language model. But essentially, it just becomes trying to sample from this distribution negative alpha times e of x. And what we find is that if we do this type of sampling, so we just take a pre-trained, we take the likelihood distribution p of x of a language model, and we just sometimes, and we just sample from the distribution p of x to the alpha, we actually find that this works almost as well as actually taking the language model distribution and running some type of RL on it to solve different tasks. So it suggests that just doing some type of sampling on this distribution is actually pretty powerful. So we find that it works, it helps in both this math data set, this coding data set, as well as this GPQA data set. And essentially, there's a bit of difference on the distribution we actually sample from. So we want to sample from, we want to essentially sample from distribution p of x to the alpha, where x is the entire language model sequence. With an autoregressive model, if you directly just sample from the logit distributions, so if you sample from a low temperature version of each of the logits, you actually sample from this this distribution where you instead you actually marginalize over the future. So it's just a different term. So it turns out that this sampling over the sum of the entire p of x to the alpha instead of these exponentiated completions of the probability distribution actually works a little better. Essentially, this procedure allows you to perform a token with many different strong possible futures, while this low temperature sampling with the autoregressive marginals just prefers to sample a token with a very high next token mass. And in terms of actually how to optimize this energy function or do this low temperature sampling, we essentially just use some type of Metropolis Hastings sampling. So we have an initial sequence, we choose some type of random cut, we resample the distribution from this random cut, and then we use the energy function to determine whether to accept or reject this change. So essentially, it's some type of Metropolis Hastings update to sample from this model. And then we can see that in terms of running MCMC steps, it roughly saturates around 10 MCMC steps. So that's around 9 or 10 times the total number of tokens generated. But we find that changing the distribution alpha that we use to sharpen the distribution actually does not really affect the performance too much, except that 2 or 4 or 8 is better than sampling from the original distribution p of x. And one interesting thing we find with this approach is that sampling from this tempered version of the distribution actually allows us to get pretty similar top k pass at k accuracy as doing some type of RL, but it allows us to preserve much more diversity as we increase the number of samples from the model. So it has a better trade-off between diversity and performance. Okay, so that was just an overview of EBMs and how you can do reasoning with EBMs. Let me know. Feel free to ask if there's any questions. So next part I'm going to talk about pretty briefly is just how you can, once you have this energy interpretation of optimization, how you can do some type of higher level reasoning over it. And one idea is that, so earlier I talked about length-driven sampling as well as this type of gradient-based optimization. One big issue with this type of gradient-based optimization is if you imagine you have these initial samples here, and you run gradient-based descent, well, it turns out that you have two minima here, but if you just do gradient-based descent, you'll never be able to actually find these global minima here if your solutions are here. So one idea is in addition to just doing some type of gradient-based optimization, you also want to do some type of more global search. So you want to do some type of procedure where you try to not only just do local gradient-based modifications, but you also want to do more global initializations of your particles. And the idea here is that so initially I'm gonna have these 4 particles, but I'm just gonna take a look at the energy values of these particles, and I'm gonna simply just discard the particles that have high energy. And this allows me to essentially concentrate my search. So I can take these particles with lower energy, I can try to duplicate them by adding some noise to them. And then this allows us to concentrate your computation on samples that are more promising or have lower energy. And there's a couple different algorithms we can do with respect to this. So one idea is we can do some type of breadth-first search. So if we have some type of diffusion inference procedure where we have a set of energy functions, I can have a set of initial predictions, which are shown as blue dots here. And then at every time step, as I'm doing the denoising procedure, I can denoise it. And then after denoising, I can compute the energy values for each of these particles, choose the ones that are most promising, and then just duplicate them. And I can just repeat this procedure where, and each time I duplicate these particles, I add some amount of corresponding noise. But this gives you a better way to try to optimize either your energy function, or if in the diffusion process, if you have some type of verifier, this also gives you a better way to optimize those verifiers. Another thing you can also do is, instead of actually duplicating the particles, you could also, if you want to reduce the amount of computation you're using, you could just simply discard the particles that have the highest energy, and then just continue with the ones that seem to be the most promising. And the final one that you can do is you can do some type of more depth-first search, where you can have maybe you have your prediction at the highest noise level. You can denoise it down to a lower noise level. And as you keep denoising it down to a lower noise level, you can check to see the values of like the energy or the verifier. You can check to see if the value is high. And if it's high, you can actually just bump up the model up a level of noise, and you can just repeat this procedure until you get overall generation that minimizes the final energy. So instead of just doing this gradient-based optimization, there's also some I guess more global algorithms that you can do at the particle level to try to optimize these systems better. And what we find is that this is really useful for these maze planning tasks, for instance. So if we want to solve a maze planning task where we want the diffusion model to generate a trajectory, but we want the diffusion model to generate a trajectory starting from this point in the maze to this point in the maze, so this is a pretty high-dimensional problem, we find that if we directly ask the diffusion model to just generate, it's very hard for you to get accurate enough sampling, conditional sampling, to be able to generate this precise path from the start state to go state. But with the series of modifications of doing multiple different parallel particles, doing some backtracking, this combination allows you to solve this reasoning problem of constructing a maze much more accurately. So we can actually, so this is a comparison of the performance in solving the maze. So this is if you only do more steps at gradient descent. So if you do more steps at gradient descent, which in the diffusion context is just some type of length-driven sampling. So if you do more length-driven sampling at each noise level, what we find is that as you increase the number of steps, you get some performance gain from 0% to around 30%. And what we find is that by adding this type of more global search-based algorithms, either this breadth-first search or this depth-first search, we find that we can get much higher accuracies to around 90% accuracy. And you can see that just simply doing this best of M sampling, where you just generate many different paths and you just choose the one that seems to be the best on your verifier, works less well than doing this type of breadth-first search or this type of the depth-first search. And this is especially true for the bigger maze. And here you can see that this type of depth-first search, where you compute the score and then go backwards, and you just repeat this process until you get a promising one, seems to work the best. And then we can also do some type of compositional image generation, where if we have a prompt, we want to have 8 bottles. If we directly just have the diffusion model generated, you generate an image of 5 bottles. But if you do this like search, where here we use a verifier that's this VLM, we can generate these images with 8 objects. Well, here if you just do the best of 16 generations using VLM, you don't actually get a generation that has this. So this procedure allows you to more carefully find a solution that satisfies the constraints you care about. And here are just some plots of this. So we tested it on this benchmark on compositional image generation, and we compared whether you just do this best of n or you do this type of pre-search or defer search under the diffusion model, and you see a much better performance per compute with the scores using this defer search or the buffer search. And you find it similarly for each of these different domains of compositional generation. Great. So that was just a pretty brief description of how you can do some of these high-level search algorithms on top of this energy optimization. So the last thing I'll talk a bit about is how these this type of energy-based reasoning procedure allows us to solve more complex problems by composing multiple different models together. Okay, so looking at the side again here. So let's say I want to do some type of coloring problem, and the goal of this coloring problem is I have this graph that's shown on the top right here, and my goal is that I want to color the nodes such that for every single edge, the two nodes in the edge have a different color. And if I want to solve this coloring problem, one way to solve this coloring problem is actually to simply learn an energy function per edge. So if I have an energy function for this edge and for this edge for every single edge in the graph, then it turns out that if I directly optimize the sum of the energy functions for all these edges, I can solve for coloring this graph under this constraint of I can solve this graph coloring problem by summing up these energy functions over the edges. So one idea is by taking energy functions for smaller subproblems and composing them, that allows us to take models specialized for solving simple problems and use them to solve much more complex ones. So here's another example of this. So here I have this n queens problem. So here I have a chessboard, and I want to place queens such that none of the queens are attacking each other. And I'm just going to learn an energy function such that it knows how to place a queen on a board such that there are no other queens that attack it. And now my goal is I want to take this energy function for placing queens on a single row, and I want to use it to solve this 8 queens problem, where now I want to place these 8 queens without any of the queens attacking each other. And the way I'm going to do this is I'm going to learn this energy function for placing 1 queen, and I'm going to sum up these energy functions over every single row in this chessboard, as well as every single column and every single diagonal. And then for graph coloring, again, I'm going to have energy function for every single edge, and I'm going to sum up the energy functions for all these edges together. And what we find is that if you do some type of zero-shot composition of these energy functions across the rows and columns and diagonals, we find that this is able to solve the 8 queens problem with 97% accuracy. And in terms of training algorithm, it ends up being pretty similar to the the training algorithm I talked about earlier about learning the sequence of energy landscapes. So so we learn a sequence of different energy landscapes, where on one hand we train the gradient of the energy landscape to be able to denoise the sample. And then we also have an additional term where we train the sum of the energy functions to ensure that that composition the composition of these energy functions actually allows you to recover the ground truth answer. And then finally, we have some type of contrastive loss, where we try to, for each of these local energy functions, we train it so that the ground truth answer has low energy, and then these incorrect answers where we have 2 queens on a row or no queens on a row has high energy. And in terms of optimization, so we combine the tricks from the first part and the second part. So on one hand, so we're going to have a set of parallel particles that we're going to optimize simultaneously, and then we're going to resample particles based off their energy, global energy values for the entire composed problem. And at the same time, we're going to have some type of gradient-based optimization at every single landscape. So we're going to do some combination of both this resampling as well as this gradient-based optimization. And here's an illustration of how the system solves the n queens problem. So at the beginning, you have all these queens at different positions. And as you run this optimization procedure across these landscapes, as well as this resampling, you eventually get a set of solutions of placing the queens on different positions by like sequentially optimizing through each of these landscapes. And you can actually visualize these energy functions. So to solve this n queens problem, we just sum up the energy functions on every single row and column and diagonal. So you can compute the energy of a particular location, for instance this location, but by just summing the energy function for this row, this column, and these two diagonals. And so you can essentially, based off this, see which positions are violating constraints. So you can see that this queen is attacking the other two queens. And what we generally find is that this approach of composing these models actually works pretty well for solving these n queens problems. Like I said earlier, it gets around 97% accuracy. You can try training these different types of discrete diffusion models as well as G-flow nets, and we find that they don't work as well in this setting. And one thing to note is our approach actually never saw any examples of the n queen problem. We only saw placing a queen on a single row. I guess the disadvantage of our approach is it's quite a bit slower because we're actually just running some type of optimization. So we actually have 1,024 parallel instances that we run this optimization over to eventually get the correct answer. Yeah, and here's another visualization of solving the n queens problem. And one thing to note is as we try to compose these energy functions, it gets harder to optimize these problems because you have more and more minima. So in practice, we do a lot of parallel particles for optimization. So we do up to around 1,024 parallel particles. And another thing we can also do is we can also use this to try to solve 3-SAT problems. And we can compare it with neural SAT solvers. And we find that this procedure with 1,024 particles, when we train it on SAT problems consisting of 20 variables and 91 clauses, we find that it gets around 99.85% accuracy. And what we can do is we can evaluate generalization to these SAT problems where there are a total of 50 variables and 218 clauses. And we again find that our approach maintains pretty high accuracy. So overall it gets harder. So it goes from 91% accuracy to around 43% accuracy. But it still generalizes quite a bit better than these other neural-based SAT solvers, as well as some of these discrete diffusion-based solvers for the SAT problems. And here's roughly a visualization of this. So our approach would learn an energy function for every single clause. So if you have a correct solution, then all the energies would be low. But if you have an incorrect solution, then one of the clauses would be high. So you can also identify whether the solutions are correct or not. And then as a final note, you can also apply this more on this planning domain. So if you want to generate a plan in a maze, for instance, you have the start location and go location, you can learn energy functions per chunk, and you can jointly optimize that. So this allows you to essentially generate these long plans in mazes where maybe each of your trajectory chunks may be a little out of distribution. So if you have some type of offline data set where your ant is just locally wandering around, it turns out that by just composing these models, you can get this much more, like by jointly optimizing for energy functions per segment, you can get this plan that goes from the start location to the go location. Okay, so overall, I talked a bit about this idea of essentially using energy minimization as a tool to do reasoning, where you can either explicitly train energy-based models, you could use existing diffusion models, or you can also use language models. I talked a bit about how you can do some type of high-level reasoning using some type of these parallel particle search-based algorithms, and I talked a bit about how you can compose multiple energy functions in order to solve much more complex tasks. Thanks everyone for listening, and happy to take any questions. Yes.
Thank you. Great talk. Very impressive. So I have some questions about this reasoning with sampling. If you have multiple modes and then you also like sharpen each mode, how fast does your algorithm mix, like the chain, the Markov chain?
So I guess we found that like the performance seemed to plateau around 10 steps of MCMC. I don't know if that's, we never really measured how far, if it actually mixed at that point, but we found like in terms of performance after around 10 steps of MCMC, it seemed to, so we had different blocks and we would run around 10 steps of MCMC per block. We found that that seemed to recover the best performance.
That's really impressive because I mean like if you sharpen the modes and then like the barrier between the modes would become harder to overcome, I guess.
Yeah, I guess actually I don't think it actually mixes. I would say like I think it finds a mode, and I don't think it really leaves that mode, especially as you sharpen it more.
Okay.
So I think it probably takes 10 steps to get to a mode. I'm not sure if it actually mixes that effectively after it gets into a mode. Yeah.
And also a follow up on this. Do you like worry about diversity? I mean like even just for like a single mode, if you sharpen it and then like you get more concentrated near the local maximum, right? So I was thinking that can you actually use what you have found as sort of like a proposal to better, like still like recover the original distribution?
Oh, so when you say recover the original distribution, you mean that you run sampling on this more like lower temperature distribution, and then you use whatever samples you get as a way to represent the entire distribution more accurately? Or?
Yeah, to represent modes in particular.
Yeah, I think that would be interesting. Yeah, because I think what we found is in terms of looking at the diversity of the pass at k, actually, this procedure doesn't seem to drop the pass at k that much. So it seems like there are a number of modes that this system is able to find.
Thank you.
Yeah, thanks. Yes.
How does the search compare to like sequential Monte Carlo?
Yeah, I think it ends up being pretty similar to sequential Monte Carlo. I think the breadth first search is like almost identical to sequential Monte Carlo. I think probably performance-wise, I think we did actually compare with a number of different sequential Monte Carlo methods in the paper. We found that it seemed to work a bit better. I think the one that's pretty different is this depth first search, where you actually go back in noise level, and we found that was the one that seemed to get the best performance. So I feel like the issue with sequential Monte Carlo is that you gradually lose all the diversity, so it's very hard for you to get a correct answer if like it's very rare. Yeah. Yes.
So you run a metropolis chain that delete all that replace all the token after some location t, right? Have you considered other type of proposal, like maybe just select a subsequence something in the middle instead of like everything after t, and like how does different choice of metropolis?
Yeah, I think that would be really interesting. I guess the issue with just replacing a subsequence is it's hard to get a consistent sequence where like after your subsequence, the remaining text is still consistent. So this is why we regenerate the entire suffix. Yeah, I think that would be interesting to do. We just never really tried it because we didn't think we couldn't figure out a way to make it so that if we only replace a chunk, the remaining chunk afterwards would still be consistent.
Okay, let's take a coffee break and then we'll be back at 11 for the next talk.